differentiability implied continuity. Okay. Their graphs will be smooth and continuous. With a well-defined slope at each point. I'm going to give you some examples of functions, okay? So i.e. polynomial, so polynomials, rationals, trig, expo, so exponential, log, and many more are some examples of functions that are differentiable. Not only that it has to be continuous at the point, it also has to have what? It also needs to have a derivative or slope, you're right. It also need to have a derivative. At the point. A comma f of a. I'm going to write this sentence and then you can tell me true or false and then it's converse. Yep.
So what are some examples that aren't differentiable?
At a point, yeah. I would totally have a problem with an absolute value function. Okay. Right, so at 0.
Stuff that has like
yeah, like our next, the second half of that, it's going to be defining all the things that you're going to have issues with. Okay. So, true or false? Here's my first sentence. If f has a derivative at x equals a, then f is continuous at x equals a. True or false? True or false? If f has a derivative at x equals a, then f is continuous at x equals a. Based on our definition, differentiability implies
yes.
True or false?
True.
True. Okay. Let me write this, and then you can tell me true or false. Okay. Different color now. If I'm gonna write it's converse. A converse means I'm switching if and then statement. If f is continuous at x equals to a, then f is differentiable at x equals a. If it's continuous at it, right away it has to be differentiable. True or false? Is the converse true?
False.
Give me an example.
Absolute value.
Absolute value, you're right. So this is false, okay? Continuous does not mean right away that it's differentiable. But if it's differentiable, it has to be continuous. A square is a rectangle. A rectangle is a square. Okay. Here are 4 cases when it is not going to be differentiable at a particular location. The first one, we're going to call this a corner. Okay. A corner is where one-sided derivatives exist, but are different. What do I mean by that? What do I mean by it exists but are different? Give me an example. Okay, fine. Since Randall loves absolute value, here we go. Absolute value of x, right? As you can see, this is going to be a V-shaped curve, right? Where's the problem really? The problem really when x equals 0, okay? Now, this is what we meant by the derivatives exist from the left or the derivative exists coming from the right, except that they are different. I'm going to start with the left first. Okay. Left-hand derivative. Do you want to do formal or derivative at a point? In this case, since we already know it's at 0, you get to choose formal definition or derivative at a point. Sure, it's really up to you. Limit as x approaches 0 from the left by definition of derivative at a point, because I know my point is 0. Is that okay? All right, this is the part where some of you are gonna be confused of this right here. What is f of x if I am approaching 0 from the left? Negative x. I'm gonna pause right there. Are you okay with that being f of x? Okay. What is f of 0 always for this question? 0. So it's negative x minus 0 all over x minus 0, which obviously the zeros are going to go on. So negative x over x, what's that? Negative 1. Left-hand derivative, as you can see, it exists, right? But let's see if it's the same as right. Right-hand derivative, the limit as x approaches 0 from the right, again, same formula. F of 0 for any side is still what? 0. But what is f of x from the right side? It's just x, you're right. So limit of x approaches 0 from the right of x over x, which is uno. 1, uno. So, derivatives, right and left, do they exist?
No.
Right and left, do they exist? Yes. Except they are not the same, just like what we stated. So therefore, there is a corner where? There is a corner at x equals to 0. Okay. So that's when it is not differentiable, and the reason is because it's a corner. Next reason that it will not be differentiable is called cusp. C-U-S-P. To get a cusp, it's when or where the slopes of the secant lines approach infinity from one side and negative infinity from the other side, or vice versa. So, I'm going to give you an example. Here we go. Something's super easy to understand. Y equals x to the 2/3 power. Okay. Some of you kind of deal with fractions, exponents better in radical form. So if you were to ask to write this in radical form, how would you write that? Okay, yeah, true. Yay, nay, maybe? What does it look like? Something square root? Is it really something square root? Does it look like an eyebrow curve? No? When x is 0, what's y? Great. 1x is 1. 1. Next nice number is what? 8. And x is 8. 8 squared would be 64. 3 over 6 is 4. Thank you. Hello.
Ryan, Bailey, or Ryan, can't see your last
Okay, so when x is 8, y is 4. I'm not going to sketch that high. How about negative? Can I have negative x values and negative y values? Or negative x and positive y values?
Yes.
Yes. Okay. It's going to look something like this. Okay. Like that. Okay. It's increasing not as fast. All right. So similarly, we are going to use limits to prove. Right or left? Which one are you going to do first? Left? None. You don't have a choice on none here. Okay. On the test, you will ask to prove these. So make sure we know how to prove it. Any one of these. I can make 4 different tests, and I can put one in each. You don't know what you're getting. You just have to know them all. Okay. Left. You get to choose. Where is the problematic location at? 0. Okay. So do you want to use formal or derivative at a point? Sure. I will let you choose as long as you know how to prove it. X approaches 0 from the left. F of x minus f of 0 all over x minus 0. What's f of 0 in this problem? 0, right? So, oh, okay. Okay, thanks. Bye. All right. Everyone say bye to Christina.
Bye, Christina.
What do you do? What class are you teaching? No, I mean, my class is just trying to avoid.
All right. F of 0 is always 0, right? So, what's f of x? What are you going to use for f of x? Do you guys have 2 different functions like the absolute value earlier? No. No. Right, because one is negative, it's positive. One is positive, it's still positive. So guess what? F of x is going to be the same for either direction or either hand derivative. Okay, so x to the 2/3 minus 0 over x. Okay. Okay, what do you want to do? I can't plug in 0 because that will give me 0 over 0. That's a double trouble. What do you do? Cube everything? Can't do that. Just like I can't square root everything. I can't go in and square, unless it's an equation. I can square right side and left side, just not top and bottom.
Can you subtract?
Rationalize it.
Can I subtract the powers?
That's the thing, right?
The bases, aren't they both x?
Yeah.
What degree is the bottom?
1,
That means I can change it into 3 over
3.
3. Yeah. Look at that. Algebra 1 coming back in style. Limit as x approaches 0 from the left. What's on the top? What's on the bottom? 1 over what?
Over x to the 1.
Correct. Okay. Then I'm going to write that in radical form because I know, like I said, some of you understand it slightly better when it's in radical form. Is that okay? Okay. Now, I still can't plug in 0 because I have then 1 over 0, which is not going to help me. But can I plug in something near 0?
Yeah.
Like what?
Negative 0.00.
Yeah, negative 0.0000. Who cares, right? Something very, very close to 0 near the left-hand side. So Mia, as 1 divided by negative 0.000001, what do you think is going to happen? What kind of infinity? Is it positive infinity?
No.
It's negative infinity, right? Negative infinity. Then right-hand side, I'm going to do the same thing. Would you agree that the math is all the same? Because I don't have to switch my f of x. I'm just going to go straight all the way down to the very last step, okay? Which is really 1 over third root of x. Now, again, similarly, I can't plug in 0. Alex, what can you plug in so I can have a visual, an end behavior, really? Can I plug in 1? Remember, I'm approaching 0, right, from the right? So what's something near 0 coming from the right-hand side? 0.00001, right? So 1 divided by something positive, super small. Brendan T. Positive or negative? Positive. Okay. Based on our definition, it's 1 positive infinity and it's 1 negative infinity. Yes or no? Yeah, so by definition, there is a what? At where?
X equals 0.
Right. There is a cusp at x equals 0. And that's how we kind of,
On the test, will we be doing it with like different functions of this or will you want?
I would translate it a little bit. Yeah. Okay, 3. Next. You're going to have practice, don't worry. Okay. So 1 positive infinity, 1 negative infinity, it creates a cusp with both infinities. Like the same direction infinity. What would you get? Well, thanks, Randall. We get vertical tangent. Remember, this we started a little bit in chapter 2, okay? But we never really finished the thought just because I knew that was coming. Is vertical tangent the same as vertical asymptote?
Yeah. Is it
Not
no?
the same as vertical asymptote. Okay. Okay, by definition, okay, where the slopes of secant lines either, approach, my bad, I should erase that. Secant lines approach either infinity or negative infinity from both sides. Okay, so not switching like the cusp, because if it is, then it's obviously already a cusp. So they're both positive, they're both negative, then it's going to be a vertical tangent. In algebra 1, if you have a vertical line, what kind of slope is that? Yeah, the slope is undefined. Remember this? Same thing. Infinity is really, does it exist? No, not really. So that's why. Okay. All right, let me give you something very, very similar to the one above. But I'm just going to call it y equals to 1/3 x. What's the difference between the two?
It's not squared on the inside.
Ah, all right. Have we ever seen this before in algebra 1 or algebra 2? Y equals 1/3 of x? Isn't this like this? I'm pretty sure we've graphed that many times, right? When x is 0, y is?
0.
When x is 1, y is?
1.
When x is negative 1, y is? Negative 1. So it looks like this, y'all. It looks pretty good from what I see. Wouldn't it be differentiable everywhere? Okay. It's under non-differentiability because there's a problem, right? What do you think the problem is at? Where it is at? Again, is at 0. I'm only taking the parent function, okay, for simplicity reasons. Translation, obviously you will move that left to right accordingly. Okay, limit. Let's use limit to prove. Left. You get to choose derivative at a point or formal. Sure, at a point. Limit as x approaches 0 from the left of f of x minus f of 0. These are all f of 0 for these are all what? 0 so far, right? Okay. All right. Oh, dang it. Yeah, Kayla, can you help me with the keyboard? Okay. So what's f of x? Cube root of x. Perfect. Okay, so limit as x approaches 0 from the left. I'm going to write x to the 1/3. Minus 0 is just going to be 0 divided by x. On the bottom, what's my exponent?
1.
1. So can I make that into common denominator of 3 over 3? Okay. When you are dividing, I can subtract my powers, couldn't I? So limit as x approaches 0 from the right of 1 over what? X to the what?
2/3.
You're right. Okay. And I think some of you will relate with radical. So here's the radical form of that. It's going to be square, not square root, third root of x squared. All right. Can you plug in 0? No, but can you plug in something near 0 on the left-hand side? Like, what's your value? Natalie, what do you want to pick on the left-hand side of 0? Left-hand side, so close. You're right, negative, right? Square that. What's happening?
Positive.
Positive. Third root of that.
Positive.
1 divided by a small positive number.
Infinity.
That's right, infinity. Okay. All right, right-hand side. Limit, I'm going to go all the way towards the end because all the basic math is the same. Limit, oops, I wrote limit twice. Okay, I have 1 over third root of x squared. Even when I pick a small positive or a small negative, when you square everything, what's happening?
Positive.
Yeah, so this is also
Positive. Infinity.
based on your definition. They both are positive infinity. What can you conclude at 0?
Vertical tangent.
Right, vertical tangent at x equals 0. So what's happening is that as you guys are getting closer, if I was to zoom in, and if you have a calculator zoom in, at x equals to 0, like the line is like this, super like that, okay? So it's super straight in that way. Okay. That's if you were to zoom in on a graphing calculator. Last one, the most obvious one. There would not be any differentiability if you have a whole is one of them. A what? Discontinuity. You are right. Okay. You are right. Because the very first thing I spelled out in differentiability implies continuity. So right away, it would not be differentiable if it's any type of discontinuity. Let's review really quickly. How many are there?
4.
What are they?
Whole.
Oscillating, whole,
Vertical.
jump, and
Infinite. Discontinuity.
infinite. You're right. Okay. So I'm going to give you this one example, and you tell me what's going on. Okay. I'm not going to define it. You already know all the discontinuity. Okay. I'm going to give you this equation, and then you tell me, oh my, negative 1 when x is less than 0, 1 when x is greater than 0. I'm going to graph it out because it's hard to see. Okay. When x is less than 1, what's going on with my y value? It's negative 1, right? It's that way?
Yeah.
I'm just graphing this out. Would you agree with that? When x is 1 or greater than 1, what's going on with my... Okay. Well, obviously, can you see that there's a jump?
Yeah.
So right away, there's a discontinuity. If there's any type of discontinuity, there is no what? Differentiability at x equals to 0. But here's the thing. Isn't the slope the same coming from the right and the left? Look at it. Look at the graph. Aren't they both 0?
Yeah.
Right? What does it matter?
No.
No, because you have a discontinuity. The derivative right away doesn't really matter at 0. Okay. Now that's going to bring me to example 1. Example 1. Okay. Can you please help me? Olivia, can you help me read example 1?
The graph of a function over a closed interval D is given. At what domain points does the function appear to be differentiable, continuous but not differentiable, or neither continuous nor differentiable?
Great. Let's answer all those. All I'm giving you is a graph with the restricted domain from -2 all the way to +3, and something breaks in the middle. Differentiable. Everywhere from -2 to +3? No, definitely not. Okay. What are the reasons that will not make it differentiable? Discontinuity. Do we have any? Yeah. So, okay. How do you want to write answer to A? No. You have to answer. At what point does the function appear to be differentiable? What point is it differentiable? It's not yes or no, but is -2 inclusive or not inclusive? Inclusive, because it's a closed endpoint. All the way to where?
To -1.
Whoa. That -1 is tricky, right? Yeah. Okay. Union that with -1 to what?
0.
What do you do?
Isn't at 0 there's a discontinuity?
Yeah.
So right away 0 there's not what? Differentiable, right? Yes. Union that with 0 to 2. What's going on at 2? It's a removable, right? Okay. Now here's the question. I'm gonna write this way, and you tell me, is that okay? That orange, I'm coloring up that bracket right there.
That's okay.
Is that okay to write like that?
No, it just doesn't only apply to endpoints.
Is that okay to write like that?
Actually, wait.
This is really okay.
I say no.
Would you agree? The way that this is written right here already tells me that is not differentiable at x equals 0, even if this is a closed bracket. Okay, because this right here is what? Open. So that means because it's not an endpoint, would you agree that this does not work, right? And also there's a discontinuity 0. So right away at 0, because of a discontinuity, the differentiability does not exist. Okay. Now the way that this is written right here with the bracket in orange right there, that is really, some teachers say, well, yes, that's okay, and some book will say you can use circular bracket. Either one is going to be fine because of the center of it. And here's why. If I were to go and just give you this and only this as a function, okay, only that piece, would you agree that you would use a bracket here?
Yeah.
Okay, because it's an endpoint. So writing this right here, it just really, because the definition of an endpoint. Does that make sense so far? It still doesn't change that there is no differentiability at 0, whether you write a square bracket or an open bracket. Now the ends are when you have to use what? Bracket if it's closed circle. Okay. So union that with 2 all the way to 3. Okay, when is it continuous but not differentiable? X equals to -1.
Yes.
When is it neither continuous nor differentiable? Do we know what the word nor means?
It's when you use or when it's negative. Or would you use neither?
Or is different than nor.
But if you use neither, you use nor. That's all I know.
It's like the word and, but like the opposite of and. You know what I mean? Like and both has to be true,
Yeah.
but like the negative of and, like both of it has to be true for me to answer this, right?
Either or, and then neither, nor. That's all I know.
I know. It's confusing. All right. When? C, final answer. How many locations? 2 at 0 and at dos. Okay. Neither continuous nor differentiable. Okay. Any question on just example 1? Let's do example 2. Find all values of x for which this function h of x equals third root of 3x minus 6 plus 5 is differentiable. Is this function continuous? Which one's easier to answer first? Differentiability or continuous? Okay, is this function continuous?
Yeah, sure.
Sure. Okay, sounds good. Yes. When is it differentiable? Everywhere? Because it's continuous? No, that's not true, right? Okay, not true. Okay, now what? Where is the problematic location? Is it 0? At x equals 0? Is it at 5? Is it at 6? Is it at 2?
No.
Okay. Would you agree that your parent function, bless you, Some of you already said it correctly. Your parent function is this, right, y'all? Okay. You're not giving just simple parent function because we did that in the notes earlier, but you're giving something with transformation. If you have transformation, you always have to factor out. If you take out the 3, what's left? X minus 2, okay? So at 2, it's where it's what? Something funny, right? Something funny happening, okay? So problem at 2. Question mark. Yes, no, maybe?
Yeah.
What kind of problem? Because on the test, I'm going to ask you what type of non-differentiability it is. It a cusp? Is it a vertical tangent? Should we prove it by using limits?
No.
By definition, what will make it a cusp? Both have to be, or one has to be what? One has to be negative and one has to be? It's vertical tangent. They both either have to be positive or? All right, so let's do it. Derivative at a point or formal? You get to choose. Okay, it doesn't matter to me. At a point.
We'll do that.
Left. Limit as x approaches what, by the way? 2 from the left. Okay, of f of x minus f of 2 all over x minus 2. Yay, nay, maybe?
Yeah.
All right, tell me what f of 2 is. 5. Yes, no, maybe? Okay, let's plug it in. Limit as x approaches 2 from the left. What's f of x? That whole thing. Third root of 3x minus 6 under the radical plus 5. F of 2 is what again? So minus 5? All over x minus 2. Oh, nice. 5's a canceling. Whoa, that's awesome. Okay, now what? Limits as x approaches 2 from the left of this thing. Third root. I'm going to factor it out to see if you can see anything. What do you want to do? Can I plug in a 2? No, that's going to be 0 over 0. That's a problem, right? What are you going to do? I mean, if only if the radical, I mean, if only the x minus 2 in the bottom is gone, right? If I don't have a denominator. So now what are you going to do? Okay. Okay, so let me try to see what Macy's saying. Okay, so Macy said like that. Take that out like that. Is that what you mean?
No, I meant multiply the top and bottom by 3. And so basically 3 would just be on the outside. I don't think that would change it. Because then you could do...
Wait, if you do that, can you just make it x minus 2 so the actual 3?
What do you mean? Say that one more time.
Like the top x minus 2, can you do x minus 2 to the 1 of the third power?
So limit as x approaches 2 from the left. So the third root of 3 stays, right?
Yeah.
And then times x minus 2 to the 1/3 divided by x minus 2 to the 3 3s. Sounds good? Okay, let's reduce. What are you going to do? What happened when you reduce? Limit at x approaches 2 from the left. On the top, I now have third root of 3. Is that okay? On the bottom, you would have x minus 2 to the positive 2/3. Yay? Nay? Maybe so?
Yay.
Good morning. All right. Can I plug in the 2 still? Still no. Oh, my. Can I plug in something near 2? Technically, though, here's what I want to bring this up to you. Would you agree that if I were to multiply, okay, can I plug in like, what's left side of 2? Not to right at 2, but near 2 on the left-hand side. Yeah. 1.999, right? Minus 2. Positive or negative? Some negative small number, okay? Let me write this in radical form because like I said, most of you identify radical as slightly better. Is that okay? Even if it's negative, isn't it squaring it? So it's going to be positive. Third root of 3, is that going to be what? Big or small? More than 1 or less than 1? More than 1. Because third root of 1 is 1, right? Third root of 1 is 1. Third root of 3, I don't know what it is. I just know it's more than 1. More than 1 divided by something so small positive is what? That is infinity. Look at that. Gosh, I stretched this page out all the way. Thank goodness for technology. Okay. I do. Sometimes it's a love-hate relationship, you know. When it doesn't want to cooperate, then I hate it. All right. Right hand side. Right hand side, I'm not going to do all the basic math over. I'm going to go straight until the very, very end because it's going to be the same exact basic math. I'm going to shoot all the way here. Third root of 3 divided by third root of x minus 2 and then square. All right, pick something positive on the right hand side of 2, like 2.001 minus 2, small or big? Square that. Small. Third root of 3 divided by something super positive small. Yep. Based on your definition, they're both positive infinity. So what? Vertical tangent at where? At x equals 2. Well, I don't think that's what it asks, right? It says find all values of x of this function that's differentiable.
No, it's just union.
Right. Differentiable at negative infinity all the way to union from 2 to infinity. And then we already answered whether that is continuous or not. All right, that is an egg roll, y'all.
Yeah.